Hello everybody, in this video I will talk about the viscosity of a fluid, which is a property of a fluid. Alright, so let's actually look at the definition of a viscosity. So what viscosity tells? So basically viscosity describes measure of fluid resistance to flow. So the idea is it will resist the to the fluid flow, and the fluids that have higher viscosity will provide more resistance. So if you think about oil will have a higher viscosity. Oil has higher viscosity compared to water, and water has even higher viscosity compared to air. So water has higher viscosity compared to air. So we do know this from our experience that some fluids will resist the flow more than the others. And again, if I look at it more closely, why is that the case? If I look at the fluid, okay, so this is a fluid element, so there are a lot of molecules inside these, and the fluids that give more resistance in fact have much stronger bonds between those molecules, so their cohesive forces are much stronger. In fact, we will talk about that once we talk about the temperature dependence of viscosity, but for now I just gave the definition, but let me get a little bit more in detail what viscosity actually defines. So before I actually start out with the fluid element, let me actually take a solid element. Okay, so if I have a solid object, so this is a solid, and this is you are sticking this solid to some surface at the bottom and a plate on the top. Okay, so now if you move the top plate, okay, or if you apply some force on the top plate, so if you're applying a force, so this block actually will see some shear stress, which actually is tau F over A, where A is the surface area of this plate. So if this is the surface area, then this actually gives you the shear stress. And the way we define, and in reality, if the shear stress is high enough, then this block will basically deform. Okay, so let's suppose this is the deformed shape, and then the change, so the deformation is represented by this theta. Okay, so now the idea is that the shear stress is directly proportional to shear strain, and this is true for solid mechanics, or anytime you apply a shear stress to a solid object, it will deform, or even if it does not, I mean, there will always be small deformation, but after a while it will stop. Okay, so the shear stress is directly proportional to shear strain, and then if I remove the constant of like proportionality, this basically is equals to G over, and the shear strain actually is gamma, and then this quantity is known as modulus of rigidity. So this is modulus of rigidity. So again, I can find this G, which is tau over gamma. So higher this value of G, so again, the higher the value of G, more resistance it will provide, more resistance it will give to shear stress. Or again, if your shear strain, which is this deformation, if that quantity is less, this means that the G will be high. So if I look at iron will have high G, or like steel will have high G compared to copper or aluminum. Okay, so this quantity basically defines the resistance that it will give to the shear stress. So this was the idea for the solid, but let's actually take a look at a fluid element. So the fluid element is slightly different, and in another video I have described the definition of a fluid. So the fluid is basically, it will continuously it will continuously um, TUOUSLY continuously deform under shear stress. So now the idea is that as soon as you apply this shear stress to a fluid element, it will continue to deform. Okay, so again, this thing is sticking with the bottom plate, and then you have a top plate, and all the molecules of this fluid element actually sticks with the bottom plate, and also they stick with the top plate because of the no slip boundary condition. Okay, so if you move this top plate with some force F, which will provide some shear stress, which is F over A. Again, this is the surface area. Now the thing is, as soon as you apply some shear stress, this will start to deform, and it won't stop, and it will just continue to deform. So in one case it will be like this, and then after a while it actually keeps on deforming to this shape, and so on. So if I look at this shear stress directly proportional to the shear strain, which actually will be represented by the changes over here, I mean, it doesn't really tell me anything. So in the fluid mechanics, and this is important, in fluid mechanics we do not look at shear strain, but we are concerned with rate of shear strain. So what it means is how this deformation is happening over time. So in some fluids it will happen faster, in some other fluids it will happen slower. So in case of oil, it will be happening slower. In case of air, it will be faster, and so that's how we we define the rate of shear strain, that over time how things are deforming. Okay, so again, what we do know, that the shear stress is directly proportional to the rate of shear strain. And again, if I have this fluid element, so let me actually give some because I want to drive this. So you have a plate at the bottom, you have a plate on the top. So now you're applying a force F to the top plate, and then this basically provides a shear stress, and then this fluid element actually deforms to this new location, and this angle I'm representing as delta theta. This distance what the fluid element traveled is delta A, and this height of this element is B, and the coordinate system y is acting this way, so y is pointing upwards. So what I do know, that the tangent delta theta is equals to delta A over B. This is just a trig identity, so tangent over is equals to delta A over the height. And for small thetas, and again we are looking at a very small time interval, so I can say that for small delta theta, tangent delta theta is approximately equals to delta theta, which equals to delta A over B. And this distance, of course, as we are applying this force F, the top plate starts moving with some velocity u. Okay, so u is the velocity of the top plate. So we can also find this distance delta A, which is equals to u times delta t. So the distance that this point travels from here to here is equals to the velocity multiplies the amount of time, and that is represented by delta t. So I can write this as delta theta is equals to u delta t over b, and then I can further write it as delta theta over delta t is equals to u over b, and I can make this limit delta t goes to 0. So what this gives me is basically the rate of shear strain is equals to u over b, and which in fact is same as du over dy. Okay, so as you will notice, as we go on the so at this point there is zero velocity, so du over dy basically is 0, but as it moves along in the y direction, the maximum velocity ratio would be u over b, which will be at a height b, and this is where you have the highest velocity u. But in between, the velocity is changing like this. If I have to draw the profile, it actually will look something like this. So on this one you have u, and then it just keeps on decreasing, and this quantity du over dy represents the change in velocity as it moves along in the y direction. Okay, and we can also write this as rate of shear strain. And what we have defined earlier, the tau is so again I can remove this proportionality, and I can make this again. So first of all, so let me write down, so tau is directly proportional to du over dy, and when I remove this proportionality sign, I will make it equals to a constant, which actually will be our viscosity, which is equals to mu du over dy. Okay, so where mu is, again, so this is mu, is called absolute viscosity, or it has other names too. It is also known as the dynamic viscosity, or simply viscosity. Okay, so so we can find, so we will talk a little bit more about that. But for the fluids, again, this is important for fluids. For fluids which shear stress is directly proportional to, or instead I should say shear stress is linearly proportional. So linearly proportional to rate of shear strain, they are called Newtonian fluids. And again, for fluids where shear stress is not linearly proportional, they are called non-Newtonian. So they are called non-Newtonian. And again, this is a very important concept in fluid mechanics to distinguish if the fluid is Newtonian or non-Newtonian. But let's actually take a little bit closer look of our viscosity and the Newtonian and non-Newtonian. So first one, I'm going to take Newtonian, and what it means is that it is linearly proportional. So if I have a shear stress on one axis and I have a shear strain on this axis, which is du over dy, which is rate of shear strain, and then you have shear stress, so the line will actually be linear. Okay, so you increase your shear stress, the shear strain will also increase. Okay, so this sort of fluid actually is a Newtonian fluid, and there actually are a lot of Newtonian fluids in the in the world that we live in. So some of the examples of the Newtonian fluids actually are oils. So most of the oils are actually Newtonian fluids. Then water is a Newtonian fluid. Then air is also Newtonian fluid. So all of them are examples of Newtonian fluids. Okay, so again, so this is a line that describes the viscosity. So let's actually look at the viscosity of the fluid. So viscosity is basically equals to, I mean, as we had defined that earlier, mu is equals to du over dy. So I'm just rewriting this expression where tau is equals to du over dy. Okay, so if I take three fluids, okay, so let's in fact these three: oil, water, and air, and we do this experiment that we apply the same shear stress. So again, in one case you have oil in between, in the other case you have water, and then you have air. So for the same force, if you apply all of this with the same force over here, which one will give you the highest rate of deformation? Okay, so in fact we do know from experience that for the same shear stress, this one will actually be it will give you the least amount of rate of shear strain. So for the oil, du over dy will be small, and then du over dy for water will be, for water is higher, and then for air is highest. Okay, so what that tells me, if this is a small quantity for the oil, so the viscosity of the oil actually is same shear stress for all of these, and now you have a smaller number. So what that tells me, that the mu oil will actually be a higher number. So that tells me the viscosity of the oil will actually be high. Then you have a middle number somewhere in between. So viscosity of the water will be less than this, but again more than what you will have for in the case of air. So if I have to write this, so viscosity of the oil will be greater than the viscosity of the water, and it will be greater than the viscosity of the air. And if I want to represent this in this shear stress strain curve, so again the one line, which is a linear line, is for any Newtonian fluid, but then I am going to draw another line and another line. So now my question would be, which of these lines actually represent oil, which of these lines represent water, and which of these lines actually represent an air? So again, this line represents oil, this one represents water, and this one represents air. And again, the idea is for the same shear stress, so the shear stress is force force over the area. So for the same shear stress, you will notice that oil will give you the least rate of shear strain, but for the same stress, water will give you more, and the air will provide you with the least resistance. So again, so this is for the air, this is for the water, and this is for the oil. And we actually found out from the definition of the viscosity. Okay, so this is the case when we have the Newtonian fluid. So what happens if we have the non-Newtonian fluid? So again, the non-Newtonian fluids actually are classified, so there are few famous non-Newtonian fluids. So again, so this is a shear stress, you have the rate of shear strain over here. So this curve somewhere over here is the Newtonian, and then you can have a curve that looks something like this, you can have a curve that looks something like this, and again these are this is another curve which is for some sort of materials that actually behave as solids for certain amount of shear stress, but once you crosses that shear stress, they basically act as fluid. and these are called Bingham plastics. BINGAM, Bingham plastics. But right now we are looking at the non-Newtonian fluids, and this is a curve, and this is also a curve that represents the non-Newtonian. But both of these have different names. This curve is called a shear thickening. Yeah, I mean this one is actually shear thickening. Yes. And this one is shear thinning. Okay, so this one is shear thinning. So the idea with the shear thickening is, so as you apply higher rate of shear strains, or in terms like if you apply a higher shear stress, which actually will result in a higher rate of shear strain, you basically will have a higher viscosity. Okay, so for high rate of shear strains, you will experience higher viscosities. And some of the examples are a quicksand, a mixture of water and sand. So the faster you want to get out from this, it actually will resist more. Another example is corn starch. So that's another example. And in fact, some of the defense projects are also so I mean people are trying to create body armors which have like shear thickening fluid. So when the bullet actually comes and hit this armor, as it passes through this fluid, because it wants to move faster, so the faster it tries to move, it will the fluid actually provides more resistance. So even in body armors, the defense are actually trying to put this shear thickening fluids. Okay, so this is the shear thickening fluid, and the opposite of that actually is a shear thickening. So as you increase your shear strain, so as you increase rate of shear strain, viscosity decreases. Okay, so as you so viscosity decreases, so the faster you want to move, the less it is easier for the fluid to move. So some examples for those are like a paint, which actually will stick with your brush, but as soon as you try to paint it on a wall, so I mean this is your brush, so as soon as you try to paint, it will flow much nicely on the wall. So the viscosity decreases as you increase the rate of shear strain. Another example is a blood. Then you have a ketchup example. Ketchup is also so as you try to move it faster, it will actually, if you increase the rate of shear strain, the viscosity actually will decrease it. And the next one, which was Bingham plastics, so they will act until some shear stress as solids, and after that they will flow. Solids up to certain stress, and after that they will flow. Okay, so some examples are mayonnaise, okay, and then again another example, let me think about it. Okay, so toothpaste is another example for those. Alright, so this is and also the SI units. Okay, let me actually make it the next one. So the SI unit for viscosity is Newton second per meter square. Okay, or English unit is pound force second per feet square. And you will notice in fluid mechanics book that sometimes there's another quantity which is commonly used, which is represented with the letter nu, and nu is defined as mu over the density, and this quantity actually is known as the kinematic viscosity. And the idea with this is, I mean, in the fluid equation, these two quantities, which this one is density, and this is your absolute viscosity or your dynamic viscosity. So these two occur so much together that you actually call this combination as a kinematic viscosity. So this is your kinematic viscosity, and so again, it basically has everything what we have described earlier. You have absolute viscosity and also the density, and the units for that is, so SI units are meter square per second, and sometimes this is also expressed as centimeter square per second. But these are the SI units. But so sometimes people also use as centimeter square per second, and this is known as a stroke, which is so sometimes people say, okay, the viscosity of this is 10 stokes, so which actually will be centimeter square per second. So again, you can either describe it as in terms of mu or nu, but they basically represent the same thing. Another important idea related to the viscosity is that the viscosity is highly dependent on temperature. So viscosity highly depends on temperature variations. Okay, and let's actually look at why is the case. So first of all, viscosity of liquid increases with actually viscosity of liquid okay so viscosity of liquid decreases with increase in temperature, and the viscosity of fluid, actually viscosity of gas, increases with increase in temperature. Okay, so let's actually take a look at it. Why is that the case, that the viscosity of liquid decreases with increase in temperature? As I mentioned to you earlier, that the viscosity basically is a resistance of a fluid to the flow. So if I look at the fluid element, in case of a liquid, the molecules are bound together very closely. I mean, so even though they are not completely fixed as in a case of a solid, but their cohesive bonds are like very, very strong, and they are, so they have a very strong attractive force. So what happens is, as you increase the temperature, the vibrational energies of the molecules basically reduces that cohesive force. Okay, so you still have the cohesive force, but now the molecules are moving with much higher velocities, so the attractive force basically is reduced, and because of that, the viscosity of the fluid basically goes down, okay, as you increase the temperature. However, in the case of a gas, the gas molecules are randomly, they are much farther apart, so they don't really see each other that much. But as you increase the temperature, so the molecule starts to vibrate with the higher velocities, and now when they are vibrating with higher velocities, they actually see each other more compared to when they are moving at a lower temperature. So the viscosity actually increases in this case. So if I actually have to draw this out, so this will actually look something like so if you have a viscosity on this axis and then you have a temperature, you will notice that the viscosity of a fluid, as the temperature is increased, it will drop down. Again, this is not this line doesn't represent for all fluids, but this is the trend that you will notice for the case of a liquid. And for a gas, you will notice that the viscosity actually the viscosity basically starts increasing. Again, there will be a slight increase, so this is the case for a gas. Okay, so this is how we actually define the viscosity, that it basically depends on the temperature. So let me actually do a quick example. So here is an example which actually I took it from one of the books on the fluid mechanics, from the Fundamentals of Fluid Mechanics by Munson. So what it says is the velocity distribution for flow of a Newtonian fluid between two wide parallel plates, which is represented by two wide parallel plates, is given by this expression: u is equals to 3v, where v is the mean velocity. So it represents that the fluid sticks with this with these walls, but the fluid velocity is maximum somewhere in the middle, and v is the mean velocity, which is an average of taking this into account and the maximum velocity. What we want to find is the shearing stress at the bottom of the plate. So we want to find what the shearing stress would be over here, which actually will be same as whatever you will have over here on the top, and the shearing stress on the plane parallel to the walls and passing through the center line. And we also want to find the shearing stress somewhere over here. Okay, so again, how we define our shearing stress. So shearing stress, so for the part A, is equals to mu du over dy, and we have the expression for u, which actually is 3v over 2, 1 minus y over h square, and so on. So I basically take the derivative of this, which actually is, so du over dy is equals to minus 3 vy over h square. Okay, so now I will plug that in. So okay, so again, so y is equals to minus h, so this gives me du over dy to be equals to 3v over h, because h is placed over here, so h cancels out with this. So it gives me a shearing stress of 3v over h. So this is for part A. So part B is also very similar. So in that case, du over dy is actually equals to 0, as you will notice that this is how the velocity profile look like. Okay, and then so this is where the y-axis was, and then you have minus h and then h, but this quantity, because we want to find out over here, so du over dy at this location is 0, as the y is 0 for this case. So the shear stress actually will be 0, and the reason being because this is symmetric, so the shear stress will be maximum at the walls, but as it starts going up, the shear stress will start reducing, and then this is where it will change sign again, so you will start to have some shear stress here, and then on this other end you will have the maximum shear stress. And lot of time you will notice that like in hurricanes or anytime there is a big storm and air is moving with a very high velocity, so what happens is it sticks with the surface, and then it basically, so with a high velocity wind, because of the shear stress, it tries to drag things along with it, and that's why you will see a lot of disaster due to wind, because the shear stress is maximum at those locations. Alright guys, so that's pretty much I wanted to say about this the viscosity. I will see you in another video on another topic on fluid mechanics.